Assalamualaikum and good day everyone. Welcome to our presentation. Today we'll be discussing the correlation between the age of marathoners and their race time in marathons. This study is part of our Sta108 Statistic and Probability coursework for the October 2024 to February 2025 semester. Before we delve into details, I'd like to introduce our team members who worked diligently on this project: Arisa Durrani, Fuada Zaira, and Isma Dayana. I would like to express our sincere gratitude for the support and guidance we received throughout this assignment. We extend our heartfelt thanks to Allah and the Holy Prophet Muhammad for their blessings. Our deepest appreciation goes to our lecturer, Dr. Noor Asiri Sakam, for her invaluable guidance and encouragement. We are also grateful to our families for their unwavering support. Finally, we acknowledge each team member's commitment and dedication to making this project a success. Moving on to Chapter 1, the Introduction. Our study's purpose is to examine the correlation between the age of marathoners and their race time. The data for this research is secondary data, sourced from the final examination paper Sta108 February 2023. It was originally collected by researchers at the Human and Sport Performance Laboratory at the University of Minnesota. For this study, the independent variable is the age of marathoners in years, and the independent variable is marathoners' race time in minutes. Our hypothesis is that age is significantly correlated with marathon race time, specifically that older age will be associated with longer race times. This is based on previous research suggesting that marathon performance typically peaks around 35 years of age before declining. Our methodology involved analyzing data from 8 randomly selected marathoners from the HSPL research participant pool, recording their ages and race times. Ultimately, this study aims to determine if the age of marathoners significantly impacts their race time. Our study has 3 main objectives. First is to determine the relationship between the age of marathoners in years and their race time in minutes. Second is to find the skewness of these 2 variables. And third is to identify, organize, and graph the quantitative data to better understand the problem and inform decisions. Understanding how age affects marathon performance is crucial. A runner's age significantly influences their race time, with both very young and older runners often experiencing slower times compared to those in their peak performance years. Age impacts key physiological factors vital for marathon running, such as endurance, muscle strength, and recovery ability. Research indicates that marathoners generally hit their peak performance in their late 20s to early 30s. Recognizing this impact allows runners and coaches to tailor running programs and optimize preparation for better marathon outcomes. Every study has its limitations, and ours is no exception. Our primary limitation is a small sample size, as the data was obtained from a course book, limiting the depth of our analysis. Secondly, because it's secondary data, we had no opportunity to clarify the data collection methods directly. This leads to the third limitation: missing context. There is no background on exactly when or how the data was collected. Therefore, we assumed the data was collected through a scientific experiment by another researcher involving a specific number of age samples with their recorded race times before the experiment.
My name is Isma Dayana, and today I will guide you through the methodology section. This chapter outlines the approach used to analyze data, starting with a detailed description of the population and sample, followed by the sampling technique and data collection methods. We'll then explore variables and subsequently graphical techniques and numerical methods to uncover patterns and relationships in the data. Moving into the data description, let's start with the population. This study focused on marathon runners aged 25 years and above who participated in a 42-kilometer marathon. This group represents the target population whose characteristics we aim to analyze, providing a clear scope for our research. The sample includes 10 randomly selected marathon runners, all aged 25 years or above. These individuals were chosen to represent a small but manageable subset of the population, ensuring we can draw meaningful insight without overwhelming the analysis. For our sampling technique, we use simple random sampling. This method ensures that each marathoner aged 25 and above had an equal chance of being selected, reducing selection bias and enhancing the generalizability of our findings to the broader population. The data was obtained using secondary data collection from a past year examination paper, specifically Sta108 February 2023 question 3. It consists of runners' age and their recorded race completion times for a marathon event, providing a reliable source for our analysis. This slide outlines the approach used to analyze data, starting with a detailed description of the variables. We'll begin by defining the key variables involved. Let's start with the first variable, age, measured in years. This is an independent variable classified as quantitative and continuous, meaning it can take any value between two specified points. It is obtained through measurement and use an interval scale which classifies quantitative data without a true zero point. Zero here is arbitrary and measures difference between values. Data were collected by recording each participant's age and are used in Pearson's correlation method to analyze the relationship with other variables. Next, we have race time measured in minutes as our dependent variable. This is also quantitative and continuous, taking any value between two specified points and obtained through measurement. It uses a ratio scale which includes magnitude, equals intervals, and a true zero point, where zero indicates the absence of race time. Data were collected by recording marathon completion times and are used in both Pearson's correlation and skewness methods to assess relationships and the data shape. Next, both age and race time are analyzed using descriptive and inferential statistics, providing quantitative summaries and deeper analysis. Numerical and graphical techniques including histograms, box plots, and scatter plots are applied to describe and interpret the data, offering a comprehensive view of the marathon runner's performance. Graphical techniques are essential in statistics as they provide visual representations of data, making it easier to understand patterns, distributions, and relationships among variables. These techniques serve as the first step in the data analysis to guide further statistical exploration. In this study, several graphs were employed to analyze quantitative data, starting with the histogram, which represent group frequency distributions of continuous data with adjacent bars reflecting class intervals and frequencies. Next, the box and whiskers plot summarize data spread and outliers using quartiles and whiskers. Finally, the scatter plot visualizes relationships between variables, setting the stage for our detailed examination in the following. Let's explore the histogram. It presents the group frequency distribution of continuous data, such as daily sales in RM, which each bar representing a class interval and its height showing the frequency of hawkers. This x-axis marks class boundaries at equals intervals, while the y-axis displays frequencies, which bar adjacent to emphasize continuity. As shown in figure 2.2.1, this design effectively illustrates the data shape, spread, and outliers, making it ideal for identifying patterns like skewness and modality in our analysis. Next, we turn to the box and whiskers plot, which visually summarize our dataset. The box spans the interquartile range IQR from the first quartile Q1 at 25 percentile to the third quartile Q3 at 75 percentile, with a median line at Q2 at 50 percentile. Whiskers extend to the minimum and maximum values within 1.5 times the IQR interquartile range, marking outliers beyond this range. As shown in figure 2.2.2, this plot enhanced by Pearson's coefficient of skewness, where 0 indicates symmetry, positive value shows right skewness, and negative values indicate left skewness. It helps detect variability and distribution of shape in the employee salary data for Company A and Company B. Finally, we use the scatter plot to examine relationships between two continuous variables. It plots the independent variable on the x-axis and dependent variable on the y-axis, displaying data points to reveal patterns like positive, negative, or no correlation. In this study, as shown in figure 2.2.3, a positive correlation is evident, with salary and car price trending upward, suggesting a direct relationship. This visualization confirms the association and provides a basis for further statistical analysis, such as calculating the strength and the direction of the association. We begin with numerical techniques, starting with measures of central tendency. The mean is described as the average of the data values, and its formula is displayed on this slide. The median is the middle value of the data arranged in ascending order, with its corresponding formula also shown on the slide. Lastly, the mode is the most frequent values that occurs in a dataset, and as you can see, its formula is here too. These measures help analyze the central distribution of age and marathon race time data, giving us a clear picture of typical values. Next, we look at measures of position. The first quartile Q1 is defined as the point where 25% of the total data is less than it, and 75% is more, with its formula for both group data presented on the slide. The second quartile Q2, also known as the median, splits the data at 50% with its formula also shown. Finally, the third quartile indicates that 75% of the total data is less than this value and 25% of the data is more, and its formulas are also available on this slide. Using this, we can assess the distribution of age and race times across percentiles, understanding the spread of data points within specific range. For measures of dispersion, we assess how data spread. The range is the difference between the largest and the smallest data values. The interquartile range represents the spread of the middle 50% of the data, and the quartile deviation is half of the interquartile range. The standard deviation is the square root of the variance. All these formulas are presented on the slide for your reference. Moving on, the variance measures the sum of squares of differences between each data value and the mean, divided by the sample size minus 1, and its formula is also displayed. Lastly, the coefficient of variation compares the standard deviation and mean for a distribution and converts this value to a percentage, with its formula also available. These measures further describe the spread of age and race time data, highlighting variability within our dataset. For skewness, we quantify data as symmetry. A positive value indicates a longer right tail, while a negative value shows a longer left tail. The formula for skewness, which use the mean and standard deviation to measure this, are displayed on the slide. This provides insight into the shape of age and race time distributions, helping us identify any skew that might affect our analysis. After that, we explore correlation to measure the strength of relationships. Pearson's product moment correlation coefficient R range from -1 to 1, indicating the strength between two quantitative variables, and its formulas are shown on the slide. The coefficient of determination shows the proportion of the total variation in the dependent variable y that is explained by the variation in the independent variable x, and its formula is also presented. This assesses the relationship between age and marathon race time, offering a quantitative measures of association. Finally, we use regression analysis to predict relationships. The simple linear regression equation y equals to a plus bx defines the linear relationship between two variables and is used to determine y based on x. The formula for the slope, b, which indicates that for each additional increase in the variable x, there will be an increase or decrease in the variable y by b unit is displayed on the slide. The intercept A, which is the point on the y-axis when x equals to 0, also has its formula presented here. These models show how H might predict marathon race time, providing a basis for further analysis. This concludes our numerical technique, wrapping up a comprehensive approach to data analysis. This concludes my part of the presentation on the methodology chapter of our study. We have outlined our data description, sampling techniques, variables, definition, and the graphical and numerical methods we will employ to analyze our data. We believe these methods provide a robust framework for our research.
Next, I will explain for Chapter 3 Result and Interpretation. 3.1 Data Presentation. Based on the data collected, both the age of marathoners and race time are considered quantitative variable because they can be measured numerically. Conversely, the participants themselves, marathoners, are classified as a qualitative variable as they can describe categorically rather than numerically. We can see that from the table, the longest race time is 250 minutes, recorded by participant aged 45 years. The shortest race time is 120 minutes, recorded by a 25-year-old participant. This observation suggests that age may be a contributing factor affecting marathon performance based on a sample of 10 participants from a 42-kilometer marathon event. Next, we move to 3.1.1, which is histogram. From the left, we can see the histogram graph for the age of marathoners against frequency. So, from the histogram above, we can identify that the mean age of the marathoners is 22.5 years. The standard deviation of the age is 6.819 years. The range of the data is 20 years. The mode of the age is 25 years, and the median of the age is 31 years. Therefore, the data distribution is skewed to the right since mean larger than median and median larger than mode. From the right, we can see the histogram graph for the race time against frequency. So, from the histogram above, we can identify that the mean race time is 181 minutes. The standard deviation of the race time is 46.056 minutes. The range of the data is 130 minutes. The mode of the data of the race time is 180 minutes, and the median of the race time is 180 minutes. Therefore, the data distribution is skewed to the right since the mean minus mode is positive. Next, we move to 3.1.2, which is box and whisker plot. This result meet the second objective through percent skewness coefficient. From the left, we can see the box and whisker for the age of marathoners. The comment for this box and whisker is the distribution of the data is skewed to the right. From the right, we can see the box and whisker for the race time. The comment for this box and whisker is the distribution of the data also skewed to the right. Next, we move to 3.2, which is descriptive statistic analysis. As we can see, these are the comments for the descriptive statistic analysis for the age of marathoners. So, for this slide, we can see the comment for the descriptive statistic analysis for the race time. Next, we move to 3.3, which is correlation and regression. I will explain for the correlation first. Firstly, we have scatter plot. This result confirms that the first objective has been achieved using percent correlation coefficient method. From the left, we can see the scatter plot of the age of marathoners versus the race time. The graph shows a positive correlation between the age of marathoners and race time. The correlation coefficient is 0.939, indicating a strong positive relationship. This means that as the age of marathoners increase, the race time also increase. Secondly, we have correlation table. From the correlation table, the value of percent correlation coefficient is 0.939. This indicates a strong positive linear correlation between the age of marathoners and the race time. The sample size is 10. Next, I will explain for regression. First, we have coefficient of determination, R squared. This result shows that the third objective was made using descriptive and inferential statistics. As we can see, the coefficient of determination, R squared, is 0.882. This means that 88.2% of the variability in the age of marathoners is explained by the race time. The remaining 11.8% of the variability is due to other factors. Second, we have coefficient table. As we can see, the value of A is negative 25.183 and the value of B is 6.344. Both values of A and B will substitute into the regression equation y equal to A plus bx. Thus, the regression equation is y equal to negative 25.183 plus 6.344x. From the regression equation, the slope B is 6.344, indicating that for every 1 year increase in the age of marathoners, the race time increased by 6.344 minutes. This confirms the positive correlation between the age of marathoners and their race time shown in the scatter plot. That we have prediction. An example of prediction by using the regression equation can be calculated as below. If the age of marathoners is 10 years, so the new race time is y equal to negative 25.183 plus 6.344 times to 10, and the answer will be 38.26 minutes.
Now, let's move to our conclusions. Key findings. Based on the secondary data, our analysis revealed a strong positive correlation between the age of marathoners and their race time. The correlation coefficient R is 0.939, indicating that as age increases, race time tends to increase as well. Specifically, for every 1 year increase in a marathoner's age, their race time is predicted to increase by 5.6 minutes. We also found that both the age and race time data distributions were skewed to the right. Implications. This understanding can be incredibly beneficial for athletes and coaches. Recognizing the influence of age on performances allows for the development of customized training strategies for different age groups. By factoring age into preparation, runners may see improved race times and overall performance. This suggests that considering age is a valuable approach for both competitive results and long-term athletic development in marathon running. This will be the end of our presentation. Thank you for your attention.